So today our topic is continuing to use Solver. Let me also open chat. Is it okay? Do you hear me and see the Excel file, right?
Yes.
Okay.
Yeah.
Nice. So this is the topic about the capital budgeting, and capital budgeting actually involves some constraints on available resources. Here is the company which initially it's the company which provides some IT services, and these IT services contain some limits for capital, and these are the available capital for each of the year 1, year 2, and year 3. And also it contains some labor constraints. Labor constraints means that this company has 900 workers, programmers, which are available to deal with different projects. So as you can see, there are 20 possible projects available here, and there are binary variable about do this project or not do this project, and this binary variable is 0 and 1. NPV is, let's say that we are dealing with this project number 2. So if the project is implemented based on the variable do it 1, then the NPV which goes to the total NPV will be 900, and it will cost this amount of dollars per year. We need to financial support, so we have to subtract from this available financial support those numbers for each year. And this project involves 139 programmers to work from out of 900 pool of workers in the first year, and in the last year 83. So the same takes place for other workers and other projects. So we have to consider calculating the total NPV, and the total NPV will be the sum product of our NPV, and either we implement those projects or not implement. So we have to, first of all, let's say that we implement only the single project 1. I will make this file available to you maybe. Okay, let me open editing. Okay. I'm just going to push the file to you. This is capital budget temp. So this file you can all open by yourself, and also the second file for today's lecture will be this one. So open this file, and you will see the same kind of budget temp. You will see the same file as I see right now. All right. So first of all, we have to calculate the total NPV, and total NPV will be the sum product of two resources, and this do it is has the name. This column has the name do it, and NPV, which is also has the name NPV. So we calculate the total NPV. Of course, now when we implement on the project 20, we have this NPV, but if we implement 2 projects, it automatically recalculates. Next, we have to prepare our constraints, and to prepare our constraints, we need to calculate the sums of, or maybe some products. We need to implement some product of our cost, and and our do it. So that means we used only 152 and 313 as we see that projects 19 and 20 are implemented. So the same kind of thing will be just stretched through all the columns, because do it has the name and it remains untouched through our other columns. All right, so as we can see, we have prepared our data to calculate. Our goal is to maximize the total NPV for the company, given this limitation on the resources. And everything is pretty straightforward from this point, because we go to data and start our solver. And inside our solver, we have the objective which we need to maximize. And we need to change cells, and these cells will be implemented over here. We either do or not doing this project. And so we need to push some constraints on this type of variable. And this type of variable should have the constraint of binary variable, because we are limited only with 0 and 1s. So our constraint, our doit, should be binary. We select here bin. And also we need to place the constraint on the amount of resources. So our resources which are used should be less than or equal to available resources. So IO with me, do you need more time? So as far as we can see, we maximize the total NPV and place the constraints on the used resources which are less than or equal to available resources, and we make our doit variable binary variable. We use simplex linear problem because we don't have any if conditions, we don't have any non-linear functions placed in our calculations. So this thing should work, and eventually it ends up with calculating some projects which should be implemented. We can see that our doit column changed, and we meet the constraints. So our used resources are less than or equal to available resources, and total NPV for this project is like this, $9,269. This is a pretty basic model, because for now we are limiting our calculations to integer values. And as you further see that integer values are much harder to calculate than regular values. That means we have to sometimes we have to change the options, the properties of our solver, in order for it to ease up calculations with integer values. Because generally, when a solver is trying to calculate something, it produces the derivatives, and going through the gradient of these derivatives to find out the maximum or minimum value or different value, as we have said. So in our case, it tries to go through the gradients, and these gradients are non-integer gradients. So it always tries to, after calculating, it tries to make the variable integers and sets the result as integer. So here in the options, we have to set the integer optimality in percentage. So do you see these options? How much percentage do you see here? What number do you see here? 5. Okay, nice. So you see, and later on in our programming, we also will share the screen so that you will see different windows. Nice. So integer optimality is 5%. That means that our optimizer tries to find integers within this 5% of tolerance. So maybe we need to make this integer optimality as 50% to make it slightly higher. And make sure that you remember 9269, this was the initial value, and once we click solver, it tries to find different value within the tolerance. For now, it finds the value which is a lot less, but this might help you sometimes when the solver okay, let us make something like 0.5, okay, and solve. So, and you can see that the length of the calculations after I click the button solve and the result we obtain, it takes some time. For now, for our run, we have a simple problem. It tries to fit only 20 lines of data to find this variable. But let's say that we have not 20 but 200 lines of data, and our problem will be exponentially grown in time. So 2 seconds will be to the exponential power of, so it will take considerably longer amount of time. Sometimes you may find out that solving such kind of problems takes maybe hours, maybe even days. And of course, it is not reasonable for us to rely on such a long time of calculation, and that means we need to change the tolerance. It helps making this percentage larger, makes us find the solution, integer solution with within a reasonable amount of time. So if your problem runs very long, stop the solver and change this value to higher values, and this will help gradually to improve calculations. Of course, the result that solver will find in this change, if you place a larger amount of times, it will be not that great, but considering the time which it took to solve, maybe seconds instead of days, it is reasonable to rely on that. Okay, basic problem is basic problem. Everything is pretty straightforward. So we may look at different constraints. So let's say that we need to implement project. If project 2 is implemented, then project 1 should be also implemented. Maybe there are some kind of projects which rely on each other, or maybe there are other constraints which rely on each other, and we have to place the project 1 less than or equal to project 2. So this project 1 is just a link to this value, and project 2 is just a link to this value. So if project 2 is selected, if this value is 1, then we can place the constraint to our project 1 to make this value as 1 also, and it makes us to implement 2 projects at the same time. Whether the project 2 will be selected, then project 1 will be selected with it. So we place additional constraint that this value should be less than or equal to, maybe even maybe more or equal to, I'm not sure. Let's start with the less than or equal to this value. Okay, and solve. Does it change in anything? It's quite awkward, but let's find out with maybe different projects. Maybe it does not select it, and just need to change the initial conditions. Let us provide the solver. Solve. Project 1 still not selected. Okay. Let us make the change more equal to 0, 0. They are not selected either. Add project 2 should be equal to 1. It must be selected. And then when we place that, our condition should be satisfied and both projects will be selected. Okay, so let me return to the initial position and make you understand what happened. So initial position was like this. We have implemented only project 19 and project 20. We provided two links. The first link is project 1, which is this value, do it 0 or 1. For now it is 0. And project 2 is the link to this project 2. Okay. Then we implemented the solver, and inside solver we placed the condition that we must select project 1. So this is the strict condition of project 2 should be implemented all time possible. Okay, so we implemented this strict condition. Then we implemented the condition that this value, which we have selected project 1, should be more or equal to this value. Okay, so if project 2 is selected, and by our strict condition it will be selected all the time, then we have to push strictly to select project 1 as well with this more equal to. We can ease up this condition by selecting less than or equal to, and then it will be considered more on the total Npv value than on just satisfying these constraints. So if we remain our more or equal to here, our solver ends up with 8874. Okay. And if we relax the condition, maybe it won't change anything, but still. Let's calculate. And it says that generally project 0 is not very good option to implement. Not very good option to implement because without project 1 we end up with something different. So let's change our project 1 and project 2 to some other conditions. Let's say project 3 and 4. And make the links to project 3 and 4 as well. Like that. Then we ease up strict condition about selecting project 2. We delete this. And this condition remained the same. So if project 3 is selected, then project 4 should be selected. And solve the problem. And our problem ends up with selecting both of the projects within the tolerance, because previously when we haven't selected, like this. Let me make this to the initial state. From the initial state, if we delete this condition and calculate, we end up with 926. What? Solver. Delete and add. This should be less than or equal to that. Okay. So our initial problem was like that, 9269, and we can see that project 3 here is selected and project 4 is not selected. So now we change our selection priority. If project 3 is selected, then project 4 should be also selected. And add this condition less than or equal to that. Okay. and solve. And we can see that 9136 slightly lower again, because of course when we place more constraints, it will be less NPV, because without any constraints, the NPV will be maximum once we select all the projects and do everything, because each project adds NPV to us, and the total NPV will be just the maximum possible value. Will be like that. It is 15033 when we select all the projects. But using the constraints, we just limit our selection options to some of the projects only. Right, and selecting project 4 based on project 3 gives us less than 9269 total NPV, but allows us to implement if this is obviously needed for the company. All right. Next, we might also produce several different conditions. Let's say that there are two groups of projects, and this is the first group of projects, and this is the second group of projects. And we have to implement at least several projects in the first group. How can we place this constraint? So for now, 3, 4, 5, 6, 7, and we may have at least how much? Maybe not at least, maybe at most. Let's make us limited from the upper side. So for now, 3, 4, 5, 6, 7. 7 out of 10 projects are selected. Let's say at most 5 projects should be selected here from the first group. How can we do that? We sum the amount of this project selected, which is 7, and place another condition, data solver add constraint. So this value should be less than or equal to 5. So at most 5 projects. Okay, and try to solve. And we can see that yes, we meet the condition of 5 projects. Both projects are not selected, but we can change that. We can change that with the strict condition add project 3 should be less than or equal to project 4. So we have to make project 4 selected strictly and try to solve this value. Okay, so at this value, project 4 is selected. That means project 3 is also selected based on our condition. At most 5, 1, 2, 3, 4, 5 projects were selected in the first group, and we have this total NPV which satisfies all these conditions, right? So once again, my solver looks like this. Do you have any questions about this? All right, if no questions, then let's move on to our second. Let's move on to our second task. And second task is involving this FinMat solver. So FinMat solver here has two problems. The first problem is PMT by solver, and we can place some kind of the rate. Let's say we're dealing with 5% interest rates monthly. So divided by 12, this is the monthly interest rate over here. PMT function. This is the PMT function based calculations on the rate. Number of periods, we have 10 months, and our value is 10,000, the initial value. So it calculates that we should pay 1023. So we can change this value to 8%, and we got exact value of the payment which stands here, which is calculated from the PMT function. So let's delete those values. Payments, delete, calculate with 5%, have this payment equal to 1, and this is our starting condition for our for our problem. So interest owed, this means we need to multiply the rate, which is rate times times the beginning balance. So this is the interest owed on $10,000, which we place over here. And ending balance will be the initial balance minus payment minus interest. Okay, so let's place initial minus payment minus interest. So we end up with this, and beginning balance equal to ending balance. So we can make those things here, and this value should be equal to 0. So let us try to find out what. First of all, we have to check whether this function PMT function works correctly, and the second one, we may implement solver to let us calculate this ending balance. Okay, so let's make us data solver. We set our objective to the value of 0, and we change payment, I guess. Change payments subject to constraints. So what kind of constraints should we place here in the formula? The constraint maybe from PMT. So we have to find out the if we place the link here, then the payment will be a link. So we need to find out the equal. Okay, we need to find the equal thing. Okay, let's close. Let us make like that. So here is the value 1, and this equals to this value, and let us make that. So we choose only this payment function in our solver by changing payment. We have payment by changing that with the condition of this equal to 0. Okay, and set objective. I'm not sure if I'm doing correctly. Let's try. So, all right, let me close this file. It found, yes, so we did correctly. So if we try to find out which value, and ends up to 0, given the payment. The payment should be all equal to one specific value, and we use this one specific value to optimize. So each of this cell is just bounded to the particular cell, given the interest rate, and we have this payment schedule, which ends up with paying everything at the end of month 10, given some interest rate. So if we change the interest rate to some other value, 0.1, let's say, we may implement the same kind of solver. Okay, column, set objective, this value to 0, solve, and we find the we find again the PMT value, and PMT value, which is calculated using our formula, equals to the payment value calculated with the solver. So everything works. It's really nice. And the last thing which I need to show you is the retire. Here we have the initial balance, we have the contribution. First 40 years, as you remember, I think we dealt with this kind of problem. So first 40 years we contribute some money, and then we withdraw that amount in the rest 20 years inside. So ending balance should be equal to initial balance plus contribution plus not plus but minus withdrawal times 1 plus return rate. So this is our formula to calculate the ending balance. So, and initial balance will be equal to ending balance. This is our calculations, and we need to find out contributions. We need to find out the contributions which ends up to this 0 value. So let's reconnect, and I'll show you how to do that.